What were you guys trying to achieve in doing some of the data comparisons between the various competing next-generation sequencing platforms?
One of the things we wanted to do was really understand exactly how all of these metrics sort of contribute towards quality. But specifically what we found that as you dig in, you actually sort of learn a lot about what each of these metrics mean. Just to give you an example, just this concept of comparing false positives versus false negatives, right? We found that, if you really think about it, there is a cost associated with getting more false positives unearthed. But if you turn to first false negatives, which are actually a lot more scary if you think about it, there is a level up to which you can actually throw more resources, through more ancillary experiments to unearth those false negatives, but some of the false negatives are actually inaccessible as well. So these are the subtleties that actually started to come out when we started really looking at these metrics in detail.
And why is there so much risk and potential, why are false negatives potentially so problematic?
If you take this into, for example, clinical environments, false positives can always be followed up. As Depesh said, there's a cost burden associated with that, but if you miss something, it could be disastrous, particularly in clinical situations. And I think for the sake of moving sequencing technology into those environments, focusing on not having or minimizing false negatives is really important.
We've had a case of a customer who gave us a tumor normal paired to sequence, and we've been quite impressed with the result. They through quite a bit of analysis, found sort of a set of markers that were very relevant to their study. When they went back to Sanger sequencing to confirm them, they actually got 100% confirmation. Pretty outstanding result.
Right, and especially as we go into the personal genomic space, right? And when you're talking about things like cancer normal pairs, the idea that you are going to miss a false negative is actually very dangerous. Kind of what I was saying before is that if there's a genetic variation there that can affect disease, and if you miss it completely, right, and that's going to have a lot more serious effects. So these are the things that we are trying to sort of unearth and sort of present as resources for our users.
And expanding on what Mark said, there's a lot of people that get excited about these just incredibly successful experiments, and there's one published every month. But I think a lot of customers, especially who are just getting into this space, are feeling like they have no yardstick to even estimate how much they're going to accomplish with a given sequencing experiment. And also, to be honest, we wanted to provide sort of a spectrum of what people are going to see in terms of how much of the genome they're going to characterize. And it's certainly not 100% every time, but it's an amazing amount of data.
You've talked about various components that assemble a holistic view of accuracy and data quality. How does that actually tie to a sequencing system? What are those various physical attributes of a system that tie to the data metrics?
On the side of optics, we've made huge improvements, leaps and bounds really, in terms of the imaging quality, the speed of the imaging, and also enabling dual surface imaging with HiSeq 2000, which was launched in January this year. On the chemistry front, we've also made parallel improvements, and we've developed a new range of sequencing reagents, the TrueSeq reagents for our sequencing by synthesis and cluster generation components of sequencing.
And what's interesting is that once you get past the optics and the chemistry stage, there is a lot that happens in the informatics stage in terms of data analysis that can actually affect the quality of your final data set fairly strongly. And just to give you an example, right, we're talking here about the most common applications. So let's say alignment and SNP calling. So if the alignment process is not optimal, or if it results in a lot of reads being discarded, then you are not going to be able to call variants. So regardless of how good the upstream processes are, if the informatics fails, then your whole sequencing experiment fails. And this, in a sense, goes back to what we talked about earlier about there being multiple metrics that add to the quality equation.
And the thing that surprised us was how important the alignability of the data was. And it starts from the data and the artifacts that are in the data, but also the methods you use to do the alignment. We saw huge differences in the completeness of the genome we got based on what input data you put in and on what alignment algorithm you use to actually look at coverage.
What's impressive is every time something new comes out, we're not sure where the benefits are going to come from. Is it going to be chemistry? Is it going to be the optics? Is it going to be the informatics? But every time the leap forward is incredible. And so certainly where it's state today, that's very impressive. It allows us to assemble very high-quality genomes. When we look at the metrics down to that detail, we really see the work of all the different components one by one. It's quite impressive.